All right, it should be up in a second, but you can go ahead and get started on your refresh your understanding. All right, when you turn to somebody near you and see if you got the same answers for this. This question asks you to think back to what we were learning about last time in terms of posteriors over what the parameters might look like for a multi-arm bandit. So check with someone nearby you and see whether you got the same idea.
Wouldn't you always have some sort of chemical balance as well? Yeah. Yeah. I think it's optimistic with respect to the first one. But it's giving it like a higher. Oh, I see what you mean.
Okay, we're going to go ahead and come back together and go through the answers for these. All right, so the first one of these are true, okay, because in this case, for beta 1, 2, where we're weighed more towards an arm that more frequently gets something like a 0 instead of a 1, then we're more likely to sample these three parameters. The second one is also true because if you have a flat uniform over all of the different arm parameters, you're more likely to keep distribution. And the third is false because when you have a 1, 1 prior, that's a uniform somewhere between 0 and 1. So you could get so the true arm parameter could be a 0 or it could be a 1 or anything in between. Okay. And then the second one asks you to think about sort of using Thompson sampling to sample arms. So the first one is true. So given these priors, you could sample either of those values for the underlying parameter for your Bernoulli variable. The second one is false. So let's assume that the real parameter here is 0.4 and 0.6. What this question is asking you to reflect about is that Thompson sampling is not guaranteed to give you an upper confidence bound. So it may instead just select a parameter that is consistent with your prior. And for these particular sampled thetas, it will happen to choose the true optimal arm for this round. Awesome, so I want to just, let's see if I can make all the AB work. I want to briefly show you this nice example. Wow. Let's see if I can make this go away. All right. So I wanted to show you this nice example of somewhere where you might want exploration. So we've talked about exploration so far in terms of cases like you're an online advertiser and you'd like to figure out which ads work for people. It comes up in healthcare. I want to show you an example of an application which we thought about in collaboration with Chelsea Finn and a bunch of wonderful grad students recently. So this is the Breakout assignment. This is an assignment that's used in Stanford where students actually encode the game. So in this case, you're not, compared to the settings we're at where you sort of assume you have the environment and then you're learning an agent to act in that environment. Here students are actually creating the code to make the Breakout assignment, so to sort of make the game environment. And this generally is often really engaging and fun for students, particularly when they're learning to program. Many people like computer games, so this is a really great opportunity for people to learn and can be really engaging. And a lot of different people use these type of assignments. So it's not just at Stanford, but many, many other places, including code.org and others use this assignment to try to teach students about programming. Here's the problem. Even though it teaches lots of different sort of introductory computer science concepts, there's a challenge, which is if you want people to learn from writing this assignment, you need to be able to provide them with feedback. And providing them with feedback involves grading the assignments. So in this case, we normally have like a rubric of different things that the program is expected to do correctly. Like, is the paddle drawn correctly? Is the ball drawn correctly? When you bounce, does that respect the desired, transition dynamics, things like that. And so normally, just like when you guys get feedback from Gradescope, someone has to go through and play the game to do this. Okay, and so that is really expensive because that means people have to figure out, okay, when the ball bounces here, does it actually do the right thing? And then you have to do that for each of the different rubric items. So there, for example, it kind of jittered, right? It didn't do the right thing. So what you can think of here is that essentially someone is manually designing a mental policy, a grader is designing a mental policy in their head for how to play this game in order to uncover whether the game dynamics are correct. And so the way we normally do that right now is, each individual grader figures out how to do that and then they play this. So this means that it would take probably around 8 minutes per submission. So you can't just do a unit test in the normal way because you actually are trying to figure out how the game behaves in different scenarios where it might take multiple actions to even get to that scenario. So if you think about sort of doing 8 minutes per submission, if you have 300 submissions in a course, and there's actually many, many more people than that that have played this game on code.org or tried to code this, that's an enormous amount of grading time. That's an enormous amount of human resource time. And that means that some of the people that offer this challenge to students don't grade it at all. Just too expensive. And so that means students get the opportunity of trying to do this exciting assignment, but they don't get any feedback back, which can be, really hinder their learning process. So there's a lot of things that make this hard. It's, sort of a stochastic setting. There's not kind of simple heuristics, and there are multiple errors. So my student, Chris Peach, another professor here, and I started thinking about this problem a few years ago of saying, couldn't we design a reinforcement learning agent to play this game? And what we want is that this reinforcement learning agent can explore the parts of the domain so that we can try to uncover how they're doing and whether the game is coded correctly. So we did this work, and then we did an initial approach to this, and then Evan, who is the key author of this, extended this to try to think about rubric items. So the idea is that instead of having humans graded, what we're going to do is we're going to replace humans by a machine learning agent. And in particular, what Evan did is he built on our and I and Chris's initial work and said, let's actually phrase this as think about how we can use meta reinforcement learning and exploration. The reason this is an exploration problem is because you want to learn an RL policy here so that in a new environment, you can quickly use behaviors to grade the assignment. And so that's where efficient exploration is coming in. So you don't want this to have to take 20 minutes to try to grade it. You want to, as quickly as possible, whether for an agent or a human, figure out what strategy you should use to play the game in order to correctly grade whether this is a good environment. And so Evan had a really nice NeurIPS paper building on our NeurIPS paper. These are both machine learning contributions of how to, there's a series of papers. There's a first paper on how we could do this at all. There's a second paper by Evan who was looking at trying to do explicit exploration, really fast exploration. And then we joined forces to think about how we could do fast exploration in this setting. And then more recently, we published a paper showing that this could actually significantly reduce grading time and actually improve accuracy when you combine this with humans. So I just give this as an example to illustrate another sort of exciting exploration case where if you can design agents that can learn quickly and can quickly explore an environment, it can end up being really helpful. And we'll come back to sort of dream and this idea of kind of meta exploration later in the course, later today. So today will be our final lecture on fast and efficient reinforcement learning. And then next week, we're going to start talking about Monte Carlo tree search, which was one of the key ideas behind AlphaGo. I hope that homework 3 is going well. Feel free to reach out to us with any questions, and feel free to come to our office hours. All right, so just to remind ourselves about where we are, we've been thinking about different frameworks for evaluating the correctness of algorithms and how efficient they are at learning and making decisions. And so far, we have focused mostly on bandits, which is this much simpler version of reinforcement learning where the decisions we make don't affect the next state. So we saw how to do that for both standard bandits and Bayesian bandits. And today we're going to start to lift all those ideas up to Markov decision processes. So we did that by design because a lot of the ideas around sort of optimism under uncertainty or posterior sampling or Thompson sampling can be lifted up to the tabular Markov decision process case. And then all of these ideas also then can be extrapolated up with some care to the function approximation setting. So that's where we're going to go today. The main approaches for trying to act efficiently in Markov decision processes, and we're going to start by focusing on the tabular setting, will again be optimism under uncertainty and probability matching or Thompson sampling. And we're going to see ideas of how to do that in this setting. Okay, so here is one of, it's not the oldest algorithm to do sort of probably efficient exploration in tabular Markov decision processes, but it's sort of one of the quintessential ones, and I think it illustrates a lot of the really nice ideas. So this is kind of a lot, let's just step through it. So the idea in this case is that we're going to be making decisions in a tabular Markov decision process. We're going to be taking actions with respect to some specific Q function that I'm going to define in a second. We'll observe the reward in the state. We're going to update a whole bunch of things, update that special Q tilde, and repeat. The key thing that we're going to be trying to do is similar to what we saw for the upper confidence bound algorithms. We're going to think about how do we construct an upper confidence bound on the Q function. So that's going to be sort of the key we're going to be doing. This is an upper confidence bound algorithm. So this is going to, again, use the idea of optimism under uncertainty, and we're going to think about how do we bring this to MDPs. Okay. So the key idea in this case is what we would like to do is we'd like to construct an optimistic upper bound on the Q function. This is a model-based approach, which means the way we're going to do that is we're going to try to construct optimistic estimates of the reward function and optimistic estimates of the dynamics model. It shouldn't be immediately obvious what it means to be optimistic with respect to the dynamics model, and we'll go through that in a minute. In practice, what we're going to do is the following. The reward is the easiest to start with. So in the reward case, we're going to maintain counts of how many times we've taken an action in a particular state. We're also going to maintain counts of how many times we've started in a state, taken an action, and went to a particular next state. And we've seen these ideas before for tabular Markov decision processes. We've used them for certainty equivalent planning back in the first couple of weeks of class. So the reward model is perhaps closest to what we've seen for the bandit before. For the reward model, what we're going to do is we're going to compute the empirical average over in this state and this action, what's our average reward we've seen so far. And then we're going to think of there being an upper confidence bound to that. Okay. What we're also going to do in this case is we're going to maintain an empirical estimate of the dynamics model. Now, when we do this, we're going to do the normal Bellman equation, except for we're going to include a bonus. So this part should look familiar to what we've seen for Hofting, which is when we are going to compute a Bellman backup, instead of like uncertainty equivalence, we would just use the empirical estimate of the reward function and the empirical estimate of the dynamics model. Instead of doing that, we're going to include this bonus term. This is this bonus term. Okay, and there's a few different ways to do kind of model-based interval estimation. I'm picking one here that just sort of uses a bonus term, but I'll talk about some other one. There's a number of variants. So what this is saying is, when I do my Bellman backup of what is the expected discounted sum of rewards from starting state S and taking action A, This is going to try to approximate Q star. I'm going to plug in my empirical estimate of the reward. I'm going to use my empirical estimate of the dynamics model. And then I'm going to add in a bonus. And if I have not taken that state in action very much, that bonus is going to be really large because those counts of the number of states and actions is going to be really small. So this will be large if the counts are small. The key difference compared to what we've seen with bandits before is this is a Bellman backup. So we will then repeat this many, many times. So you do this for all states and actions, and then you back up, and you do this many times. So intuitively what's happening here is this is like pretending the expected discounted sum of rewards you'd get if you start in a particular state and take a particular action is much higher if you have not visited that state in action very much. So that's where this optimism comes in. You end up adding in this bonus term here, and this bonus term will be really large, so beta is defined up here. This bonus term, this is a 1 over 1 minus gamma. So if you imagine that all rewards are scaled between 0 and 1, and gamma is really small, you can think of that as kind of being like h times that sort of special term divided by the square root of the number of times you've been in that state in action. So what that means is when you do these repeated Bellman backups, it will drive your policy to visit parts of the state in action which you have not visited much. Okay, because those are the parts where you're going to have these really large overestimates, probably overestimates, optimistic estimates, I should say. You're going to have these optimistic estimates of how good the value could be in those states. And the reason this is important is because it might be, so this is going to work when you're doing sort of a series of episodes, or you're working in the same MDP for a long time. What will happen is that you will explore in your MDP, and it will drive you to cover the state in action space if you think that, that it might possibly have good rewards in those places. So this will drive exploration. And by doing these repeated backups here, you're propagating your optimism under uncertainty backwards so that you develop this policy to drive you that way. So this is one of the quintessential algorithms for doing tabular optimism under uncertainty-based planning. It is also a PAC algorithm. So we talked about PAC last time. In PAC it means it's probably approximately correct. I'll just write that out again just to remind ourselves. Probably approximately correct. But now we're going to talk about, in particular, Markov decision processes. So we talked about how an algorithm is probably approximately correct if most of the time it makes a decision that is close to optimal and only makes mistakes on a polynomial number of times. So we talked about that last time. We saw that you don't have to guarantee this. You could make mistakes forever. Like if you're acting randomly, that's not you would continue to make mistakes forever. MBIE-EB is a PAC algorithm. So what it says is that let's let sort of script AT denote MBIE-EB's policy at time step t and ST denote the state at time t. With high probability, the value of the action the algorithm takes is at least the value of the optimal action for that state minus epsilon, and it's true on all but a finite number of steps with high probability. So this is the number of steps. Okay, and the important thing here is this is a polynomial in the size of the state space, the action space, 1 over epsilon, and 1 over 1 minus gamma. Now, I always encourage my research students to plug in for bounds because theoretical bounds are beautiful, but it's nice to know whether or not they are at all related to practice. So for example, in this case, you might imagine, let's say we have S equals 10 and A equals 10, okay? And you've said epsilon is equal to 0.1 and gamma is equal to 0.9. All right, so let's just work out what that would be. That would be roughly 10 to the 3 times 10 to the 9, or 10 to the 12. So that's a lot, okay, right? So what that would say is that we are sure by using this algorithm that we will only make mistakes on this 10-state MDP 10 to the 12 time steps. Now, I don't know about you, but I would hope that in, a 10-state grid world MDP, that we could learn to act substantially faster than that. So I use it to highlight that these bounds, while this might officially say this is a pack algorithm, they can be pretty conservative in sort of how many mistakes you might make. Now in practice, often this optimism under uncertainty algorithm can work very well. It doesn't say you will make this number of mistakes, it just is an upper bound on it. But it's good to plug these things in just to sort of see how tight or not you think it is relative to real performance. All right, so this is a pack algorithm. The paper goes through an interesting proof of it to sort of show the different components. But one of the key ideas is something called the simulation lemma. And that I'm going to go through at least briefly, because the simulation lemma is one of the many core ideas when we think about doing efficient exploration. And the key idea for the simulation lemma is the idea that we can relate the accuracy of our models to the accuracy of our learned Q function. Okay, so that's the key idea. It's going to say if we have bounded, yeah, I guess I'll just leave it there. So we can bound. There's sort of a really if we just ensure that we have good predictive models, we can relate our error in our predictive models back to our value function. So let's do that at least, sort of sketch. So this is going to be for tabular settings. Okay. So we're going to assume that we're back in like a finite set of states, finite set of actions. Okay. So this is one proof of the simulation lemma. We're going to assume that we have pi as a fixed policy. And we are going to assume that we have a max norm on the reward. So we're going to assume, if you remember back, let me do R1 minus R2. We're going to assume that we have two different MDPs. So MDP1 and MDP2. And these might have slightly different reward functions and slightly different dynamics models. So remember that if we have the infinity norm, we can express this as like, this is going to be the place where the two reward functions differ the most over our finite state space. So, if one of them gives the rewards of 1, 2, 7, 3, and the other one gives the rewards of like 2, 6, 1, 7, we would figure out for which state do the two rewards differ the most. Let's assume that's upper bounded by alpha. We're also going to assume that we have an upper bound on the dynamics model. Okay? So we're going to assume that T of S prime given SA minus T2 of S prime given SA is also bounded. I'm going to assume that's bounded by beta. Okay. So that means from the point of view of your predictive models, the two MDPs differ by, you can bound the amount. And we're going to show if that's true, then we also are going to only differ in their estimated Q functions for a particular policy by a bounded amount. So what we have is we want to compare what is the Q value of under model 1 for state SA and then following policy pi versus Q pi 2 of SA. Okay. And the reason this is going to be important is because in general what we're going to have is the R1 and R2 are going to correspond to our uncertainty. So if you think back to the Hofting inequalities I told you about, we talked about how our empirical estimate could differ from the true estimate by a bounded amount. So that should make you think about this part. R1 could be our empirical estimate of the reward, and R2 could be the true unknown one. And Hofting can give you an upper bound on what that alpha is. And similarly, we can get a bound on the dynamics model error as well. Okay, so the idea will be to say, if you end up plugging in, say like an empirical estimate of the reward model and the dynamics model, how far away could your estimate of the Q function be from if you actually knew the true reward model and the true dynamics model? Okay, so that's why we're doing this. Okay, so this is the difference. Let's just write down what that will look like. So this is going to be R1 of SA plus gamma sum over S prime T1 of S prime given SA D1 pi of S prime, okay, minus R2 SA plus gamma sum over S prime T2 of S prime. And just use the definition of the Q function there to write out what is the difference between the two Q values. Okay. All right, we're going to upper bound this. Okay, as follows. We're going to just use the triangle inequality first. Okay, so we're just going to say this is less than or equal to R1 minus R2. So I use the triangle inequality plus gamma times the difference in the second terms. This should hold it in parentheses. I just use my triangle inequality, I split the two terms. Okay. Remember this, we've already said is going to be less than or equal to alpha, because we've upper bounded our error. So then we have to think about the second term. Then we're going to do something that we often do in reinforcement learning, which is we add and subtract 0, or we add 0, and we're going to do that by trying to relate between. Right now we have the dynamics model of one thing, the value under the dynamics model of model 1, and the value function of model 1. And so now we want to have some in-between terms so we can directly think about the difference in the value functions under one particular dynamics model and the difference of the dynamics model separately. Okay, so what we're going to do in this case is we're going to say this is less than or equal to alpha plus gamma, and then we're just going to add and subtract some terms. Okay, so sum over S prime, and I'm just going to use shorthand here so that I can fit everything. Okay, so I'm just going to introduce add and subtract 0. Careful with make sure that's clear. Okay, so I added a new term, that is kind of this intersection term, and I added and subtracted it. Okay, and the reason that's helpful is now I can just think of terms where they only differ in the dynamics model or terms that they only differ in the value function. Okay, so this is going to be less than or equal to alpha plus gamma times sum over S prime, T1 of S prime times the absolute value of V1 pi prime SV2 prime, okay, plus gamma times sum over S prime, T1 of S prime minus T2 of S prime. All right, so what have I done there? I've just rearranged the terms. I just moved these two here, and then I moved those two there, and I'm starting to apply my absolute values a lot to just repeatedly do the triangle inequality. All right, so what is this? This part looks a lot like this thing. Okay, so that's going to be like a recursive term. Okay, so we can turn this part into the following. This is going to be, this part here will be less than or equal to alpha plus gamma. Let's call this difference delta. Okay, I'm going to call that delta. Okay, and then if I do that, I have sum over S prime just T1 of S prime. Okay, so this could just be like a max difference in your value functions. And then the second term I have, I'm going to use the fact that my value function is upper bounded. So here, R max divided by 1 minus gamma. So if you get the maximum reward at every single time step and your discount factor is gamma, this is an upper bound on V max. So that allows me to take this term out, and then that just leaves me with my difference in my dynamics model. Okay, so I have this. And that was this term. Okay. All right, so that's what I have in this case now. And so this has to hold for all states and actions. So here, here the delta that I've defined. Delta is kind of like the worst case error over any of these, right? So over any states, what's the maximum difference between the value functions? So that also has to hold on the Q side. So we get this, we get delta is less than or equal to alpha plus gamma delta plus gamma V max beta. I'm going to subtract that, so now I have 1 minus gamma times delta is less than or equal to alpha plus gamma V max beta. Or delta is less than or equal to 1 over gamma alpha plus gamma V max beta. Okay, what have we just shown? We've said the worst case error in the value function for the same policy between one model and the other model is upper bounded by 1 over 1 minus gamma times the error in your reward model plus gamma times your maximum value times the error in your dynamics model. So that is one version at least of the simulation lemma. It comes up in lots of different other areas too. People use it for a lot more advanced, complicated settings. But the critical idea here is to say, if you can bound your error in the dynamics model or the error in your value function and the error in your reward function, that also means that your Q functions can't be too different. Okay? So that's the main important point of that. And so this idea in general is a helpful one because it means as we explore and we learn these predictive models better, we can be sure that our value function is also simultaneously getting better and better over time and getting more accurate. And in the proofs of PAC algorithms, that's often used to say you can't sort of infinitely learn in particular states and actions and not end up with a value function that is getting more and more accurate. Okay. All right, so now I'll pause there in case anybody has any questions before we move on to Bayesian Markov decision processes. Yeah.
So here we define the difference in the value function as delta, but why we could also represent the difference in Q function as delta?
Yeah, because we end up, we use this has to hold, this is an upper bound to this term, and this has to hold for all of the states and actions we could ever be at. And that also has to hold for this, for any state. So you could make A here be pi of S, and that, so then,
should there be a factor of the number of states because we're summing over all the states, or is that because just from the error bound, I thought that's just for one state. For example, the dynamics, just for one state is less than or equal to beta, and then in the proof it's summing over a bunch of states.
Good question. So what happens here is this is just assuming that given you have a bound on this, like for every single, like this tells you this is for every single S prime, you have a bound. What will end up coming, normally where the number of states will come in is when you start to think about how much data you need to achieve this. And you want this to hold for every single state action pair. And normally that's where you will end up getting a dependence amount of data in order to get sufficiently small confidence intervals and with your union bounding to make sure all of these bounds hold. In terms of this part, the state space doesn't appear. Okay, but this is just for the simulation lemma. It doesn't then tell you all the way to how many samples you need to achieve this. Okay, that's sort of another part of the proof. You could probably imagine already, given what you know about Hopting, that you could imagine having some way to compute how many samples you need to get alpha sufficiently small. And the dynamics model kind of takes a similar idea. And you can do this for other sort of parametric models too, like Gaussians, et cetera. Anybody else have any questions on this part before we go on to Bayesian? All right, let's step on to Bayesian. Okay, so this is some of the, so in all of these cases, we weren't using any notion of priors or any of the things that we saw last time. So now we're going to think about how we can lift some of the ideas we saw from last time to think about this for Markov decision processes. So just as a refresher, remember the other way we can think about this, a common way to think about trying to do efficient exploration is to imagine that we have some prior knowledge over how good we think different states and actions might be or how we think the dynamics might work. And then what we're going to do is try to use that information to figure out how to act. And we saw Thompson sampling as being one method that was an efficient way to try to make decisions when we have these priors and these posteriors. Okay. And now we're going to think about sort of lifting these ideas to the sequential case. So what we saw before is that we'd have these priors over the model parameters, like in this case, say the reward models, and that if they were conjugate, then after we would actually observe a reward, we had this nice closed form expression for the betas. So we could think of these as just being kind of the number of successes and the number of failures. And I talked about, but didn't actually illustrate, that you can do this for other sorts of things like Gaussians, etc. All right, so you might think this should work clearly for the reward part of the of a Markov decision process. Can we do this in general? So this is what we did, just again to remind ourselves that Thompson sampling for multi-arm bandits involved us maintaining this prior. We would sample from that, meaning we would get like a particular set of values for our coin flips, like what you saw before. We would then act optimally with respect to those, observe a reward, and update our posterior. So now what we're going to do is a very similar thing, but we're going to maintain priors over Markov decision process models. So we could have a reward model, and this right now we're going to again start with the tabular case. So we're going to start with the tabular case. There's a finite set of states and actions. So in this case, you could imagine maintaining a different reward model for every single state and action, and being able to sample from it. Okay, so you could sample like a parameter for every single one of those. And we're going to see how we can use that to actually do sort of something very similar to Thompson sampling for the sequential process case. Okay. So the idea now is that we're going to maintain a prior over all of the dynamics models and all of the reward models. We will sample from that. Now, if you remember what I just showed you, in the case of bandits, once we did the sampling of the parameters, it was really easy to figure out a decision. Because we just, in the case of the Brunskill bandits, as soon as you know that this coin flip, is going to give you one with higher probability than this other one, it tells you how to act. For a Markov decision process, it's more complicated because as soon as you see the dynamics and reward model, you don't know how to act yet. So you actually have to solve a planning problem. So it's like you sample a Markov decision process. Once you're given that Markov decision process, then you have to do planning, like value iteration or something like that, to actually get your Q star. Once you get your Q star, then you can sample, you can select the optimal action given that computed Q star. So computationally, it can involve a lot more work than what we saw in the Bandit case. Okay. Then the next question you might have is, how do we do this sampling? Okay. So this is the PSRL algorithm. It was invented by Ian Osmond and Dan Rousseau and Ben Van Roy, who's here at Stanford, and these guys were here at Stanford when they invented it. The idea is as follows, and I'll talk about sampling the dynamics model in a second. There's going to be a series of episodes. At the very start of an episode, given your prior, your current posterior, you are going to, for every single state action pair, sample a dynamics model and sample a reward model. Given that, you're going to compute Q star for your sampled MDP. Once you have that sampled MDP, you are going to act according to that policy for the entire episode. So this computes a Q star for the entire episode. You're then just for t equals 1 to h, you're going to assume your episodes are finite. You're going to act according to your Q star, observe your reward in your next state, you're going to repeat. Okay. At the end of the whole episode, you're going to take all of the data that you just got, and you're going to update your posterior. So for the reward model, it can be very similar to what we saw last time, where you just sort of update your counts. For the dynamics model, it's probably, it may not be clear what you would do in that case. So in this case, what we would often probably choose to do all right, let's right up here. So what we would often do is we'd use a Dirichlet model. A Dirichlet model is a conjugate prior for a multinomial. Okay, multinomials is what we can use for our normal dynamics model here, because a multinomial allows us to express what is the probability of going to any of the next states given this current state in action. So in general, we would have one multinomial for each state in action pair. We are now in the Bayesian setting, and so we would have one per SA pair. Okay, and this specifies our probability distribution over all the next states. That specifies P over S prime given S and A for all S prime. Okay, and it has to sum up to 1. That's the multinomial part. The part where we're being Bayesian is we're assuming we don't know what all these parameters are, and so we have a prior over them. And the Dirichlet is a conjugate prior, which means that if we start with the Dirichlet over multinomial parameters, we observe something. So let's say we're interested in understanding what happens when we're in state 1 and we take action 1. And we observe that we go to S3 7 times. And we observe we go to S7 3 times. Well, I'll do 2 times. What that means is that at the end of that episode, we would use that data to change our Dirichlet distribution over those multinomial parameters. Very similar to what we saw for the beta distribution, okay? And I don't expect, it's an interesting thing to do, but I don't expect you to do that in this class. Some of you might want to for part of your projects. But the key idea here is that it is conjugate. So it means that the posteriors you get are in the same family as your priors. And so you can use this to sample multinomials. Essentially, it's just sampling dynamics models. So we do this in this case, and we do this over and over again. And the really key things to notice here compared to what we were seeing before is that we have to sample this entire MDP and we have to compute its optimal value before we act. So we do all of this computation before the start of an episode. And you might, yeah.
I'm a bit confused about this sampling the MDP, but then sampling dynamics and reward models part.
Oh, this is just explaining that.
Okay.
This is like a comment. You sample the MDP. What this means is just for each of the state and actions. Yeah, good clarification question. To sample an MDP, what I mean is that you're going to define the MDP. So that means we can completely specify an MDP given a known state and action space and a discount factor by specifying a dynamics model for every single state and action pair and specifying a relative model. Okay, and then we'll have to compute the optimal action. Now, one thing that you might wonder about is it important or necessary that we do all of this once per episode? Okay. So when we talked about Bayesian bandits, after every single observation, we updated our posterior. So we would, try buddy taping the toes, and we'd see that helped someone recover, and then we would update our prior. This is a bit different, right? We are only doing this every 8 steps. Now, you might think maybe that's computational. You might think that that's being done for another reason, but it's something that that's an interesting thing to think about. Let me see if I have this on the next slide. Yeah, so let's do a check your understanding, and then I'll talk a little bit more about why this is done in PSRL. So this asks you to think a little bit about sort of doing strategic exploration in MDPs and in Thompson sampling in the algorithm I just showed. Okay, why don't you compare your answers to someone near you? Thank you. Okay, yeah, so now it should be back on. What I was saying is that in Maria's Demopoulos' work, she was thinking about concurrent reinforcement learning, which is something we've also thought about. And for this much more realistic setting, the idea is whether you might need to coordinate exploration and how frequently you update. Now, one of the challenges of this setting, even before you get into concurrent reinforcement learning, is that if you update your prior a lot within a task, like within a single episode, you're essentially sampling different MDPs within the same episode. The reason that can be bad is it now is going to totally change your behavior, and there may be some cases where you essentially thrash. So let me give an example. So one of the sort of canonical hard Markov decision processes that people talk about is a chain. Okay, it's really just sort of like an illustrative one. And there are lots of different slight variants of chains. And the idea is that you might have something, I've shown stuff that's similar to this before, where, on one side or on the other side, oh, it's not reconnecting, just for in the back there, you need to reconnect, that you would have high reward on one or the other sides. What you could imagine in this case, if you were thinking about it being like a Bayesian bandit, is that some of the times it might pick a Markov decision process where this is the best state, and some of the time it might pick a Markov decision process. Oh, it's still not showing on the, there. Thanks, hopefully that'll come up. And some of the time it might pick one that is here. So if you start off acting, let's say that you first sampled an MDP, where this is the best state, you do your planning, and then your agent's going to start going this way. Okay. Let's say you observe that there's some zero reward here, and your Thompson sampling updates, and now it says, hey, this is the best state. Okay, because you just have some prior over the model parameters, and so your agent turns around and it's like, oh, I shouldn't go this way, I should go this way. Okay, and then as you're doing that, it's getting more rewards, and it's updating its posterior, and so then it samples again, and it's like, oh, this is good. And so it can lead to this kind of thrashing behavior because it's sampling a new Markov decision process each time, and so your agent can end up kind of toggling back and forth between its sort of ideas over which MDP it's in. So it's for this reason that often you will want to essentially commit to the Markov decision process you're in for the whole time. You don't always have to do this, but that's one of the reasons why this can be helpful.
This commitment is also in like the 2013 NURBS paper well, not paper, but the algorithm that we saw earlier, right? They both commit?
This is just exactly the same as the PSRL algorithm. I'm about to tell you about the seed sampling, but yes, this is just in the 2013. So yeah, exactly. This is the, in PSRL itself, it commits. And this is one of the reasons for that. And so in Maria's work, she sort of discusses some of the important benefits of it. And then she thinks about how would you actually maybe try to couple and coordinate exploration if you have many agents that are going through the same environment at once. And it's for sort of in some ways like, it relates to this idea too. You might want everybody to sort of commit to exploring different parts of the space, because if you have many agents in the same domain, you might want to say, you're going to think that the best reward is here. You're going to think the best reward is here. Go explore, and then we'll sort of unify our posterior afterwards. So she has a nice demonstration of that, and then she extended it to the deep learning case shortly afterwards. But maybe if I come play that. Okay, so eventually it happens, right? But then you can get to concurrent UCRL, where in this case, it's much, you can start to, if you don't do something smart, again, this can end up being not very effective. And let me just see if I can skip ahead to the last part. Seed sampling, okay, good. Okay, so seed sampling in her case is what they're doing when they essentially do concurrent reinforcement learning. And you might have even missed it because that part is really fast. Okay, so I'll move it to this just so I can talk over it at the same time. Okay, so this is seed sampling, which is what their idea was. And this sort of just talks again about doing strategic coordinated sampling. So you can see in this case, we're leveraging the fact that you've got concurrent agents that are exploring the environment. They're committing to it, but they're committing to it in a way that they coordinate that so that you don't get all of the agents. So here by 324, all of the agents have shared information about where the cheese is and everyone's solved. Okay. All right. So that just illustrates why you both need sort of this committing to a particular exploration strategy. And then if you're in the case where you also have concurrent agents, which is very realistic, then having this additional coordination is really helpful. Now, I think one of the interesting things to note there is that this is a nice place where there's some, is it connecting? Hopefully it'll connect in a second. Where there's an interesting disconnect between theory and experiment. It's still not, maybe there's like a problem with the connector. We'll try to get that fixed for next week. There's a disconnect between theory and practice because theoretically, you don't need to do this exploration. So we have a paper from 2015 showing that if you don't do coordinated exploration, it's still totally sufficient. You can still get basically almost a linear speed up. But, oh good, found the game, yay. All right, so that covers sort of how you can do Bayesian exploration and sort of optimism under uncertainty in the tabular Markov decision process case. But of course, what we'd like to be able to do is to do this for much more large state spaces and realistic problems. So this is a very much an ongoing area. Again, you'll see this sort of similarity to the types of ideas we've seen before. Very popular ideas are optimism under uncertainty and Thompson sampling. They're not the only ones, but they're probably the dominant strategies people try to use.
Sorry, I may have just not caught this, but like what is actually different between the two algorithms? Like what is the difference in like seed sampling, like between 2013 and 2018?
Yes, so two things. One is that the PSRL does not think about concurrency. So they just assume there's a single MDP, you have a single agent in it. The other case assumes you have like M agents all in the same MDP. So like the mice trying to find the cheese, there's not just one mouse, there's a whole bunch. And the idea with seed sampling is also to think about how do you choose which MDP they each think they're in to distribute the exploration.
Okay.
Yeah. Okay, in the other case, you don't have to do any coordination because there's only one agent. Okay, good. So in terms of generalization, we're going to think about this. The reason why this starts to get more tricky is a couple things. One is that for optimism under uncertainty, it means we have to have a notion of uncertainty. And it just gets much harder to represent uncertainty when we have deep neural networks. Similarly, for Thompson sampling, as we start to move up to really complicated domains, we need posteriors over really complicated settings, and that's also computationally challenging and hard to approximate. Okay. So let's first start with contextual bandits. And some of you guys will probably be doing some of this for your project. So instead of having our multi-arm bandit, now we're sort of halfway between a Markov decision process and a bandit. So we're going to assume we have states, but the action we take doesn't influence the next state. And so now if we think about rewards, we'll have a reward per action and state. And just like what we've often done before, if we have a really large state and action space, we're going to assume that we use some sort of parametric representation to model the relationship between state and action and output rewards. Perhaps not surprisingly, there is an enormous benefit of doing this. So if you think about a setting where this is the number of arms you have, okay? If you did something like upper confidence bounds, and this is regret is on the y-axis. So if you did something like upper confidence bounds and you have 1,000 arms and 4,000 pools, sorry, you have 1,000 arms and then you're pulling these over time. So this is, I think, just regret after a fixed number of time steps. Unsurprisingly, if you have a lot more arms to pull, you'll have a lot more regret. Because in upper confidence bounds, in the things we've seen so far, you don't share any information across the arms. If, on the other hand, you use something like linear UCB, which assumes that your arms are represented by a set of features, so showing someone, like a Trump campaign today and a different Trump campaign tomorrow might have the same effect, because they're going to have a shared set of features. About Trump, at least, would be one thing that would overlap. You can leverage that structure. And so what you can see in this case is that if you leverage sort of like, say, a parametric linear representation in this case, even as you scale up the actual number of arms, if your parameter space is still the same, then your regret doesn't scale badly. So for example, so this is K, but your theta in this case, your theta in this case might just be low dimensional. So we might have sort of a theta, which is in RD. So we have a d-dimensional representation. Okay, and this just shows that this can be really helpful. Like in general, you want to leverage structure. So one common thing to do is to model the reward as a linear function. Of course, this could be built on top of a deep neural network or on top of a large language model or something like that. You can often just use some really complicated representation of the state and action space, and then say, for the last layer, my actual reward is going to be a function of these complicated features dot producted with some theta parameter. And one common thing is to assume that it's just this linear function plus some noise. And the nice thing about this is that if your features are interpretable, then your reward function is also very interpretable, because you can just think of like relatively how much do each of those features contribute to your reward. All right. So one thing to think about in this case is in these settings, well, I'll go a little fast through this part because I want to make sure we get to the MDP part too. But when you have this, even if you have kind of a linear set of models, you can use them to represent sort of more complicated functions. Because let's say technology is against it. So let's say this is your reward model. Okay, for 3 different actions. This is A1, this is A2, and this is A3. And this is what your reward is. And this is your state space. Okay. So let's imagine that you had a linear representation. Then you could represent policies that are disjoint linear. Because you could, if you were taking the max here, this is what the value would be of your policy. Because it would say A1 dominates for this part of the state space, A3 dominates for this part of the state space, and A2 dominates for this part of the state space. So linear ones, I guess the main point here is that even if you have a linear reward model, it doesn't mean your policy has to be linear. Your policy will be disjoint linear. It can be made up of these sorts of functions. Okay. So it's fairly flexible. Okay. How would we work in these cases? Well, in this case, what it means to have uncertainty is we need to have uncertainty over this linear vector. So we want to capture uncertainty over theta through some sort of uncertainty set. And there's been a lot of beautiful work to try to quantify the types of uncertainties we have through things like the elliptical potential lemma and things like that, which give us basically just sort of an uncertainty set over vectors. Okay, and you can do this in a computationally tractable way. And what this means is it gives us a principled way to get an upper confidence bound on the reward function, given that we have uncertainty over linear model. And this was shown to be very useful for news article recommendations about 14 years ago. And you can also look at chapter 19. So these are really useful. This is one way to sort of represent a contextual bandit setting when you want to handle generalization. We'll now talk briefly about how you might do this for Markov decision processes. Okay, so if we think back to the MBIE-EB algorithm for finite state and actions, we have to modify a few things. Okay, so if we think about this, we were keeping track of counts. And we were doing this, we were building a model separately for every state in action. So this count-based term here that we're using as a bonus, we've already seen how we might be able to do Q functions with like deep neural networks, but the big problem here is the count-based bonus. Like we have an infinite number of states. If you think about Atari or something like that, you certainly don't want to count. You're mostly only going to see one Atari screen once ever. And so these sort of count-based bonuses aren't very realistic. And so we're going to need ways essentially, but why do we have the count-based bonuses? We have the count-based bonuses to try to quantify our uncertainty over how well do we know the reward model for this particular state and action, and how well do we know the dynamics. And so one of the ideas when DeepRL came around was to think about, could we lift this idea and try to quantify our uncertainty in the DeepRL setting? Okay. So we're going to need to move beyond having these very simple counts to think about something that's sort of a higher level representation of that. Now, if we could get that, and I haven't told you how we can get it yet, you could imagine that a lot of the algorithms we've seen before could be extended fairly easily. So in particular, if you think about something like function approximation with Q-learning, we could imagine just adding some sort of bonus term in here. So instead of having our empirical reward plus gamma times, our target, like our observed next state in action with some, parameter weight, we could just plug in some bonus. That's kind of what MBIE-EB is already doing. It's just that our bonus before was determined by our counts. And now we need some other way to lift that so we can do that for much more general settings. But once we have that, we could imagine plugging it in here. Okay. So there's a lot of different approaches that have been developed to try to think about something of sort of density or quantification of how many visits we have or how much certainty we have over different parts of the state and action space. So one of the things that Mark Bellemare and others did, which was pretty successful, is they tried to build sort of pseudo counts over parts of the state and action space. So you can imagine maybe you've been some particular rooms in a video game many, many times, and so you try to essentially reduce your uncertainty over those. There's all sorts of important details here around like whether you, normally in MBIE-EB, every round you update all of those counts. In reality, if you think back to deep Q-learning, we maintained a buffer of state, action, rewards, next states. Now you would need to include those bonus terms in there too. And if those bonus terms are changing, how much do you update your buffer? Just to give you a sense of some of the different wrinkles one has to think about. Okay. But the high level important thing is that this matters a lot. So in Montezuma's Revenge, which was early on considered one of the hardest Atari games, probably still is, if you did sort of just standard DQN for 50 million frames, which is a lot, it never got past the second room. It just, with epsilon greedy exploration, it was not strategic. It just got very bad performance. But what Mark Bellemare and others showed is that by incorporating sort of a notion of count-based lifted to the generalization case, you could do far, far, far better. So that's just to highlight that there are ways to lift up this notion of sort of optimism uncertainty for this type of setting. There is similarly ways to lift Thompson sampling. So we've done some work there where we think about sort of particular representations and parameters. Ian Osband, who introduced PSRL, then tried to lift it up to the deep Q-learning case. They did it where they were just bootstrapping samples as an approximation. That is a pretty coarse approximation of uncertainty. Something else that often worked pretty well, surprisingly well given how simple it is essentially to do something just at the last layer. So at the last layer, do something like Bayesian linear regression to try to get an uncertainty estimate, and then sample from that. So this is a pretty simple thing one could try. There's a lot of work to do this. Let's go back to thinking of other really recent approaches which try to think about doing this not just for one task, but many tasks where you need to do generalization. So early in this lecture, I introduced the DREAM algorithm to you, which was we later used to actually do grading of the breakout assignment. The notion in DREAM is that you have many different tasks and you're going to learn how to explore in them efficiently. So that was one example where we're now really thinking about how do we develop efficient exploration strategies by leveraging structure over the tasks, where an agent is going to do a series of tasks. Similarly, in some of our recent work, we introduced decision pre-trained transformers. This was, again, a meta-learning case. The idea is that your agent's going to do a series of bandit problems or a series of RL problems, and we want to learn how to optimally explore in those settings. So I'll just show you briefly kind of how it works. The idea in this setting is we're going to use a pre-trained transformer. One of the interesting things is you can map reinforcement learning to supervised learning, similar to behavior cloning, but instead of relying on the data you collected in the past, if you can compute what would have been the right action to take there, you can train it to predict that optimal action. It turns out that when you do that, we can exactly map that back to doing the equivalent of Thompson sampling. So in all the settings for which Thompson sampling has theoretical guarantees, this decision pre-trade transformer can inherit those guarantees, which is pretty cool. The nice thing too is that empirically it can allow you to take advantage of structure that is present in your domain that you didn't have to code. So let me just give you an example of that. So what I showed you earlier in this lecture is that if you have a domain where you have some linear structure, if you give that linear structure to your algorithm, then you can do quite well. So that's the green line here. So this is the amount of data you have over time, and this is your cumulative regret. Lower is better. So most historical algorithms have assumed you give that structure to your bandit. Like, you write down, oh, there are these 300 features that you need to pay attention to news articles and people to figure out what the reward will be. If you give it that structure and that structure is right, you often do pretty well. You could not leverage that structure and you would get something like this. Okay, so this is a Thompson sampling algorithm, which just assumes that it doesn't have that linear structure. One of the cool things that we found by this approach is that in this setting, if you really have a linear structure in your domain, and you're doing many tasks and all of them have this linear structure, what our decision pre-trained transformer will learn is that even though you're not telling it, it will realize it can more compactly encode that structure. And so when you deploy it on a new task, you will get behavior almost as if you gave it the unknown structure. So I think this is really interesting because often one of the brittle aspects of machine learning is that we originally wrote down these sort of representations. And of course, one of the really amazing things for deep learning is that we're trying to not write down specific representations as much and get much closer to the input raw data. And this is illustrating that in terms of sort of sequential decision making and meta exploration for multiple tasks, we can do something similar here where we can sort of inductively learn that that's a more compact way to represent the domains and get this sort of much more efficient exploration in new tasks. All right, so just to conclude, we're wrapping up our notion of sort of data efficient reinforcement learning today. You should understand sort of this tension between exploration and exploitation in reinforcement learning. I haven't used these words, they're not great words, so I don't use these, haven't used these a lot in there, but exploration meaning you're taking time to learn about the domain, exploitation meaning that you're leveraging that information to make good decisions in the context of reinforcement learning. You should be able to define and compare different sort of notions of good, whether like empirical, convergence, regret, and pack. You should know for the algorithms we've talked about, do they have, for example, is greedy sublinear regret, which it's not. You should understand sort of the proof sketch I did of why upper confidence bound is sublinear in regret. All right, and then next week we're going to talk about sort of AlphaGo and how do we think about doing smart adaptive tree search in really large games. See you then.